Then let's welcome our second speaker. So it's Daniel Egger from IBM, and he will talk today about atoms, how we can go through this, and then what we can do with it.
Right. Thank you very much. Hello, everybody. So I'm from IBM Quantum, based in Zurich. And today I'll be talking to you a little bit about some of the topics that we find interesting at IBM Quantum. Of course, this will heavily revolve around digital quantum computing. So maybe to first start off this talk, I just want to give you the mission statement that we have at IBM. The goal is to bring useful quantum computing to the world, so by providing digital quantum computers. And then the second one that we also have at IBM Quantum, but I won't be talking about, is related to cryptography and quantum computing. So maybe first off, why quantum computing? Why do we find this interesting, and why are we looking at it? We know that there are a lot of problems that we can very efficiently address today with classical computers. Archetypical example is if you take two numbers, you can very easily multiply them. Now, it turns out that the converse is difficult. I give you a very large number, it's difficult to factor into its prime components. And this changes with a universal quantum computer. So this was shown back in 1994 by Peter Shor, who developed an algorithm showing that you can efficiently factor a number with a quantum computer. And so there is then a scope of problems that we hope to address with quantum computers. So before I get into the talk, I want to give you a bit of an outline of what I will show today. The first off is I want to give a brief introduction to quantum computing, how it works, what principles it relies upon, just to bring everybody up to the same page. And then I want to talk a bit about the applications of quantum computing. And so here you might think that, of course, if the computer is quantum, you can easily simulate, let's say, quantum systems. So that's an obvious application. I will be talking about applications in different domains just to show something different. In this particular case, we'll be looking at how one would solve combinatorial optimization problems on a digital quantum machine, and then also a much longer term application, namely financial simulations. How could you actually use such a machine in the context of finance? And this is also a topic that I find particularly interesting, given that before joining IBM, I also worked as a risk manager in the finance industry. Now, as mentioned in the title, I also want to talk a little bit about the software stack. So the Quantum Information Software Kit, which allows us in the community to control these quantum computers. And this is also a nice segue into a Qiskit community project named Qiskit Cold Atoms, which tries to, let's say, abstract the control of certain cold atom-based experiments in the language of quantum circuits. And so basically the goal here is to have a little bit of a discussion around some of the topics that we find interesting at IBM. So without further ado, let's start with a short introduction to quantum computing. Now, if I look at a classical computer, you all know how that works. We have information stored in bits, 0 and 1, and then we process this information with gates, as shown here. Now, in a digital quantum computer, we want to process information using the laws of quantum mechanics. So, of course, this means that we need to have a quantum bit. This looks like this. It's a system of two states, 0 and 1. Any physical system that realizes this could be used in practice for quantum computing. Now, the way that we depict quantum programs is typically with a quantum circuit. I'm sure that you all know this. Each wire here corresponds to a quantum bit, and then the operations here, they correspond to quantum gates, which are in fact unitary matrices that manipulate the quantum information. So a few examples here, you would have Hadamard gates, which allow us to create superpositions of states, and then this here corresponds to the controlled NOT gate, which flips the state of one qubit conditional on the other one. And then, of course, at the end, you need to measure, you need to extract information from your quantum computer. Now, what is interesting is that in quantum computing, you can build up large superpositions of all the different states in your basis. But when you measure, you will end up collapsing this large superposition onto one basis state. And the probabilities that you get out depend, of course, on the coefficients here in your superposition. And so this means that when you look at a quantum algorithm, the quantum algorithm has to do something clever to focus, let's say, the right solution that you're interested in on the bit strings that are, let's say, the solution. So maybe scaling up a little bit, we just talked about superposition, but there is also entanglement that can be leveraged in quantum computers to introduce, let's say, correlations between your different units of computation. So a quick example, I can go through this pretty quickly because I'm pretty sure that everybody's familiar with this. But if I take a system with two quantum bits, I have four possible states that can coexist, 0, 0, 0, 1, 1, 0, and 1, 1. And then depending on the values of these coefficients here, I might have entanglement or not in my system. So here's an example of a few states. The first one is not entangled, and the next two are entangled, meaning that we have correlations between the two. It's fairly easy to see why this would be the case for us physicists. If I have a system that I can write as a product state like this, going from here to this, then it is not entangled. But if I cannot do that, then we basically say that we have entanglement between our qubits. And you can quite easily understand this, right? When the first qubit here is in state 0, the other qubit is also in state 0. However, if the first qubit is in state 1, the other one is also in state 1, right? So this shows correlations between these two quantum bits. Now, as I mentioned before, a quantum algorithm needs to do something a little bit more intelligent in order to, let's say, beat, for instance, classical. And this is what I will start depicting here in the next slides. Let's just assume that I have a system with 3 quantum bits. I have 8 possible states, and I'm in a scenario where this state here, 0, 1, 0, corresponds to the solution of some problem that I'm trying to solve. All right. So if I prepare an equal superposition of all of these 3 states, like this, and I measure, I will get each outcome with a probability of 1 divided by 8. And at this point, I haven't done anything better than a classical sampling. So we need to be a little bit more clever. And one of the algorithms which allows us to do this is Grover's algorithm. What happens here is we have an oracle, which effectively marks one state with a phase. It doesn't know what the solution is, it's just able to recognize it and marks it with a phase. Now, if I were to measure from this state, I would also get each outcome with a probability of 1 divided by 8. So once again, I haven't done anything better than classical sampling. Now, where the trick comes in is that you can interfere these different probabilities by reflecting through this new line that you see. And when you do this, the blue bars decrease and the red one increases, as shown here. And so now if I measure the state of this system with a much higher probability here, I will get the state 0, 1, 0. This shows a little bit how, by manipulating these states, I can favor the one that I'm actually interested in, or which corresponds to the solution. And this principle is kind of used in some of the applications that I'll show, one of them being to measure risk quantities. So a quick overview of what the technology actually looks like and how we build them. Inside our systems, we use superconducting qubits. So superconducting qubits, they are small electrical resonators formed of a Josephson junction with a capacitor in parallel. Now, these systems need to be placed at very cold temperatures in order to cool them down to their ground state and prevent fluctuations from the environment. It's why we operate in dilution refrigerators. And these allow us to effectively reach temperatures of around 15 millikelvin, which is cold enough for us to operate. The technology looks fairly complicated, but it's been around for a long time, and it is also extremely reliable, meaning that once I have wired up my system, closed it off, and cooled it down, it can stay cold for months on end. Now, when you look at the fridge here, it's very busy, there's a lot of cables and so on, and this is because we need to bring in the microwave signals into the devices to be able to control the qubits, and then we also need to read out, meaning that we have lines which will take the information from outside to inside. So a deeper look at the technology. if you look at a quantum chip and you zoom on it, you will basically see a few types of elements. The first ones are the quantum bits, as you can see here. And the other ones here would be resonators, which allow us to either couple the qubits or to read out. Now, the resonators, these can be very simply viewed as an electrical circuit of a, sorry, down here, of a capacitor in parallel with an inductor. This forms a harmonic oscillator. Then you can also see, because it's harmonic, it's not really a great system to process information, because if I drive one transition, I end up driving the whole ladder of states. And this is why we replace the inductor here with a nonlinear inductance named the Josephson element. And this allows us to introduce a nonlinearity in this potential. And this nonlinearity leads to a ladder of states here that has different spacing between them. And therefore, I can selectively address this transition. The transition is located at around 5 gigahertz, and this means that we can conveniently use conventional microwave technology to do so. Right? So this is very, very important. Also, you can convert this frequency into a temperature, and you get a temperature of about 240 millikelvin. And so this already means that if you want to be able to cool this to the ground state, you need to be at temperatures much lower. Hence, the dilution refrigerators that I showed in the previous slide. So I want to show a picture here of what it actually looks like to have a larger quantum system, larger quantum chip. I'm showing here the Osprey device that we had on the cloud last year for maybe 6 to 7 months. And it is a digital quantum computer with 433 qubits, right? So that's already quite a large number. Now the chip is arranged in 3D. So you have a plane here where we have the qubits, which store the information, right? If you look closely, you can kind of see them here, arranged in a nice lattice with some coupling elements between them. Now, on the plane below it, we have the readout. So these are the readout resonators. Basically, every qubit is coupled to a harmonic oscillator, and depending on the state of the qubit, you get a frequency shift on that harmonic oscillator. And by probing that harmonic oscillator with a microwave pulse, you can get different properties for transmission and reflection, which allows us to infer the state of the qubit. And then the lowest plane here are the drive lines that come to control these qubits and then also to read them out. So keep in mind, this requires a lot of classical control electronics around it. Basically, every qubit needs to have at least 2 microwave drive lines coming in. So in effect, when you look at a chip like this with on the order of 400 qubits, this means that you have on the order of 1,000 or so arbitrary waveform generators controlling this device. Right. So what can you do with these? I want to give a quick overview of some work that my colleagues did in Yorktown last year. And what they were trying to do is to show that you can produce something on these machines that is very difficult for a classical computer to do. So this was published in Nature. And it's kind of one of the papers that is trying to brush on, let's say, performing computations with a quantum computer that a classical machine cannot do. And so they tried this out. Basically, it looks like this. They have a quantum circuit, we show here. It is hardware native in the sense that we only apply 2 qubit gates between qubits that are natively coupled. And the model is in some sense inspired by an Ising-Hamiltonian. It's a very restricted version of an Ising-Hamiltonian. And so what they do is they perform some kind of a trotterized simulation on this lattice. So it is a simulation with 127 quantum bits. So referring to the talk before, this already gives us a little bit of an idea of how tough these things could be when you simulate them. Now, with classical machines, you can try and simulate these with tensor product-based methods. So you can see here, these would be, for instance, these red curves. And depending on the type of observables that you measure, right, so X, Y, Z, and the different correlators between them, these could be rather difficult or rather easy to calculate on classical machines. And so they did here a simulation with a depth of 20 layers of Protest steps. So it corresponds to about 60 layers of CNOT gates. They started investigating this on the quantum computer. You can see that if you try and measure this, you get the green dots down here. This is because the quantum machine is quite noisy. But we have a lot of methods to error mitigate these machines, right, to bring these expectation values back to where they should ideally be. And the error mitigated points correspond to the blue ones here. And there are some regimes for this where you can calculate this exactly, like at the edge points here. And then in between, my colleagues were arguing that the classical methods tend to fail to simulate these quantum circuits. So they published this out on the archive, and now, of course, each time you try and do something better than classical gets to have its own go at the problem and try and do what you did at these scales. And this is effectively what happened. So after the paper was released, a few weeks later, we had lots of classical papers coming out showing that, no, you can indeed simulate these circuits. And I think this is beginning to come into a very interesting regime where we start touching a little bit on areas where we can do stuff with these quantum machines that is very hard to do classical. And what I find particularly interesting with this back and forth between the quantum and the classical that happened last year is that a few different papers came out with all sorts of different new methods to calculate the expectation values that were presented in this circuit. What was particularly fascinating is that all these classical methods and the quantum, they tend to agree with each other up to about 20% or so, right? So there is no exact simulation that can reproduce what the quantum computer was doing, right? So in some sense, this is what a lot of the people at IBM like to refer to as the beginning of the area of utility for quantum computing, where we can start to do things that become hard for classical. So this particular example is still somewhat contrived. And a lot of the research that we do in Zurich is to try and look at quantum algorithms and try and see how they could also be useful in a practical setting, right?
Which is the quantum?
It's the quantum are the blue dots here.
And the blue dots.
Yeah.
This is the experimental machine.
Exactly. This is the experimental machine, indeed.
They're all, yeah.
The different are the different classical methods. Okay, so before I dive into the applications, I want to quickly show and discuss the roadmap that we have at IBM Quantum to scale these technologies. I think it's a fairly ambitious roadmap, but still a very nice one to have, and so far we've been delivering on it. So the roadmap has several components to it. One is scaling up the hardware and the technology, shown here with the different systems. And the other one is a bit more on the software side. So maybe for a bit of context, when I graduated from my PhD about 10 years ago, the state of the field was the following. Superconducting qubit devices were in the realm of university groups, with the state of the art being maybe 5 qubits on a chip, more or less. And since then, we have come a long way. For instance, now we have machines with 133 quantum bits available 24/7 on the cloud. So there's a lot of scaling that has happened, right? And this was sort of enabled by having the vision in this roadmap that I showed here. So you can see that now in 2023, we've got on the cloud systems with about 127, 133 qubits, and we want to scale up towards error correction, right? So we know that these quantum systems are noisy, the gates are not perfect, they make errors, and therefore, if you really want to have a universal quantum computer, digital machine, you need to have error correction. In error correction, we encode one logical quantum bit in multiple physical qubits. So this has a very large overhead, and this is why these qubit numbers need to scale up. And you can see here a little bit the goals that we have, where here we would have 200 logical qubits, and in 2033 and over, this would be 2,000 or so logical qubits. If you look closely at the roadmap, there's different technologies that will enable us to get there. For instance, we would have multiple quantum chips, smaller ones, first connected with classical links and then connected with long-range quantum couplers. And so this modularity is also something that helps scale up these systems. So with that, I want to dive in now to some of the applications that we have. So this is, of course, only the tip of the iceberg. There's a lot of research in this particular field. The first one is combinatorial optimization. What exactly does that mean? What we are trying to do is to solve a problem of this form, where we have a quadratic form, and we have decision variables here, the x, which are binary. They take on the value 0 or 1. There's a lot of different settings where these type of problems appear, both, let's say, in operations research, but also in practical industry settings. A very simple example is in the context of finance, portfolio optimization. The idea is I have a set of assets in which I can invest. I want to try and maximize the amount of money that I'm making. And so which assets should I select or not select? You can formulate this as what is called a Kugel. Classically, it's a problem that is NP-hard. It's also very difficult in quantum. And the algorithms that I will show now in quantum, they are what we would call heuristics. There is no proven speed up over the classical or advantage, but it basically gives us an extra tool that we can use to try and tackle these problems. And keep in mind also that a lot of classical solvers that are used to solve these type of problems, like Cplex and Gurobi and so on, they are also based on heuristics, extremely efficient heuristics. So how do we do this on a quantum computer? Well, we need to translate this classical problem into a language that the quantum computer can understand. So the first thing to do is we convert our binary variables to variables that take the values -1 and 1. So when a physicist looks at this, you would immediately go, aha, this is starting to look a lot like spins. So what we do is we replace these variables, Zi, with Pauli spin operators. So we now have terms of this form, which correspond to the tensor products of different Pauli matrices. And if I play this substitution game in this problem here, what I will end up with is a Hamiltonian. And this Hamiltonian has the nice property that the solution to the classical optimization problem is in fact the ground state of the spin Hamiltonian. So now I have translated this combinatorial optimization problem into a ground state problem. And the way that we can do this is we prepare a quantum state on the quantum computer, and then we sample from that state. This will give us bit streams, right? As I measure the qubits, I get zeros and ones out. When the quantum state is nicely prepared, I should be able to find good solutions to this problem. A quick example here. I have two decision variables, x0 and x1. This is the form that I'm trying to minimize. The solution to the problem is this state here. It's the one that has the smallest value of this cost function. And then when I translate this to a Hamiltonian, I get a matrix, which is 4 by 4. And the ground state, the one with the lowest energy, also happens to have the values 0 and 0, which is this particular point here. So, as mentioned, a very popular class of algorithms that has been researched and is being researched quite intensively are these variational algorithms. I have a parametrized quantum circuit. So the operations, they depend on parameters, beta and gamma. And then I will try and optimize these parameters in such a way that I minimize the expectation value of this Hamiltonian. So I'm trying to minimize the energy. We therefore have a loop between the classical and the quantum, where the quantum prepares the quantum states, we sample from it, we construct this expectation value classically, and based off of these measurements, we adapt the parameters in order to try and move towards the ground state. So this is what is known as the quantum optimization algorithm, quantum approximate optimization algorithm. There are many, many papers discussing this. Here I'm showing one of our colleagues where they sort of add a twist on how you would sample the energy. What they're looking at here is a small scale problem of 5 financial assets, and you want to try and select the best ones based on some budget constraint that you have. For instance, here, let's say we invest in only 3 of these assets, and we try and optimize the return while minimizing the risk. And so this works. This is evaluated on hardware at a small scale. Of course, 5 assets, you could probably almost do that by yourself on pen and paper, right? So this is also why going forward, a lot of the work is on scaling these systems. Now, At IBM, we also like to partner a lot, not only with academia, but also with industry. So this is one first example of this where we partnered with Barclays here. So the first author is from Barclays. And we looked at a problem that they found relevant for the financial sector, namely transaction settlement. What we have here is a clearinghouse, a financial institution, which receives trades from different parties. And then the clearinghouse has to determine how to match these trades. So this is once again a combinatorial optimization problem, but it comes with some twists that you also have continuous variables in here. And so we did a little bit of research and a bit of work together and figured out a way how to use these variational algorithms to tackle problems like this. Now, as mentioned, combinatorial optimization is applicable to many different fields and of broad interest in both academia and industry. So if you're interested in reading a little bit more about this, there is this large working group with 31 different institutions covering academia and industry, which published a white paper on this last year. It's kind of intended to be a little bit of a paper to highlight, let's say, the challenges in the field and maybe some of the potential way forward. Now, we mentioned finance in the context of, let's say, combinatorial optimization. I want to show something a little bit different here. The application that I'll be talking about is a lot longer, further away in time. The setting is the following. We have some kind of a portfolio, or maybe some assets that we might be interested in either buying or selling. If you're a trader, let's say, you'd be interested in how much should I pay to buy this asset. If you're a risk manager, you're more interested in how much do I stand to lose on a single day, right? If the markets fluctuate, how much monetary value could I have to lose? Now you can measure this with different quantities, like the value at risk. This is none other than a fancy word for the quantile of the lost profit distribution of the portfolio. So for instance, the 95% value at risk tells you that in 1 out of 20 trading days, you will lose at least as much as the value at risk. The way that financial institutions approach these problems today is often with Monte Carlo simulations. You have random variables, for instance, interest rates, that go into a model of whatever financial product you are interested in. And then you draw samples from these, and you try and estimate these quantities. Now, since you are doing Monte Carlo, the confidence interval on the quantity that you are estimating scales as 1 divided by the square root of the number of samples, meaning that if I want to increase my precision by an order of magnitude, I need to increase the number of samples by 2 orders of magnitude. Now, on the quantum side, we have an algorithm which is called quantum amplitude estimation. It allows you to estimate a quantity, and basically the confidence interval that you have scales as 1 divided by the number of samples. So if I want to increase the precision by an order of magnitude, I need to increase the number of samples only by an order of magnitude. So if you compare the quantum and the classical, this corresponds to a theoretical proven quadratic speedup. This is kind of what is starting to show up here in this particular slide, where you can see that the estimation error decreases faster on the quantum. What I would like to point out here is that methods based off of this are far out in the future, because you need to have a very large number of logical qubits. So if you remember the roadmap before, we had around 100 or so physical. And so to run something like this, I would imagine that you would need at least 1 million or so physical qubits, right? So there's still some scaling that needs to be done. So keep that in mind. Now, this is also something that interests a lot of our partners. For instance, JP Morgan Chase was interested in this, and we collaborated with them for a while to come up with a framework to price options, so derivative contracts on these computers. Basically, a lot of the work here was done just to figure out what the circuits for these things might look like. So this once again shows a little bit the way that we leverage our network to collaborate. The first work that we did was based on Zurich, showing that you can actually use quantum amplitude estimation to evaluate certain risk metrics. And then collaborators in KO, they produced a twist on the algorithm, showing some improvement, right? So research into quantum algorithms can directly improve applications. And then we leverage these two pieces of work in this collaboration to come up with this framework for pricing options, right? And then all of this was contributed back open source to the Qiskit quantum information software kit. Once again, keep in mind, seeing something like this work in practice is still decades away, right? So a long time. A quick overview can be found in this particular piece of work here, where we discuss different applications. So here we talked about optimization and simulation, but of course, a lot of research has been done into how to use quantum computers to, let's say, aid in machine learning tasks. So with that, I want to talk a bit more about the software stack, and then I will transition into something a little bit more closer to the people here. So to control these quantum computers, which are available through the cloud, you need to have the software stack that allows you to do this. And for us, this is Qiskit, the quantum information software kit. It is developed open source and has a lot of different components to it. We have simulators of quantum systems, and then we have hardware providers. The hardware providers, these provide you with, let's say, a connection to the different machines, right? So of course you have hardware providers for the IBM machines, but also then other vendors, like for instance, Alpine Quantum Technologies, which is a startup based in Innsbruck. They build quantum computers based on trapped ions. And so they also have providers for Qiskit. Then the core capabilities in Qiskit is what we would call Qiskit Terra. This is what allows you to build the quantum circuits, which will then be executed on the hardware. It allows you to go from a high-level description of a quantum algorithm down to hardware-native instructions that the machine can execute. This, of course, means that you need to take into account restrictions of these machines, like the limited connectivity between the different qubits. For instance, my quantum algorithm might want to have an operation between qubit 0 and qubit 50, but perhaps on the chip there is no direct connection between the two, and so you need to start swapping the information around. And then building up on this core here, we have lots of different high-level application modules, like for instance, Qiskit Nature to simulate natural systems. And then we also have a few sort of lower-level applications that allow us to, say, simulate dynamics of quantum systems, like the time evolution of a Hamiltonian under a certain pulse, and then also Qiskit experiments, which allows us to go and benchmark the quality of these computers. So in a nutshell, this is what it might look like. At the top level of the stack, you have an application. We discussed, for instance, optimization. And then we need to translate this into a set of circuits that we can run on the hardware. So this is the act of transpiling. We go from a high-level description of the quantum algorithm down to a lower-level description that the machines understand. And then this quantum circuit needs to be translated into control pulses, which then go and drive the quantum systems, right? So for instance, the microwave pulses that drive the superconducting qubits. On this level, you'll also find in other technologies like trapped ions and so on. Now, we're trying to abstract this a little bit into what we refer to as Qiskit patterns, which is kind of a framework for dealing with applications that run on quantum. The first step is to map classical inputs to a quantum problem. The next one is to optimize the problem for execution. And then how much more time do I have? Okay. So then going through this fairly quickly, when you look at it at the combinatorial optimization, you have a translation of your classical problem to the circuit. We transpile this and optimize it for the hardware. We run it to get out the different bit strings, and then we translate these bit strings back into a solution of the classical problem. Now, in the next few minutes that I have, what I want to do is to discuss a Qiskit community project, which is called Qiskit Cold Atoms. And what we are trying to do in there is to abstract a lot of cold atom simulators in this quantum circuit language, and then also provide providers that people could leverage to give access to these systems. So You can find this on GitHub. It's open source. It features tools to control cold atomic setups through Qiskit. It has simulators for qubits and fermions, and a provider to interface with these backends if somebody wants to create a backend for these systems. So the idea is a little bit the following. In the quantum circuits that I've shown up to now, every wire has been interpreted as a two-level physical system. So we changed this interpretation a little bit in this package. We recognize that wires have internal states and that a measurement on such a wire will yield one of these internal states. And so basically the type of measurement in the physical setup defines what the wire is. And then the gates in a lot of these setups are simply the time evolution of a Hamiltonian. So basically we will view quantum gates here as being generated by Hamiltonians. So this is kind of the platform. If you go and look at the documentation, it would look like this. But I want to give a little bit more insight as to what type of systems we are actually trying to describe. And this was also done in collaboration with people at Heidelberg University. So what we have is we have fermionic tweezers in one of the settings. So we can describe where you have fermions that might hop around in a lattice. And then the wires, these describe the different fermionic modes that you have in this system. And then the unitary operators here, they correspond to the time evolution of the Hamiltonian that the system is providing you. And so you can kind of abstract this, and you will have different types of gates that you can do in these tweezers. So for instance, you can have hopping where you manipulate the potential a little bit so that the fermions can hop between different wells. You have an interaction gate, which allows you to have two of these fermions interact. And then also what we call here spin flip gates. The experimental status, for instance, based on research done at Heidelberg University, is to have typically 3 to 4 tweezers. And then, hey, we have a bit of an idea of how fast these can be. Why people like these systems, of course, I think you know this very well, is it provides you with intrinsically fermionic Hilbert space to work with. The other space which is supported by this package are the collective spins. So what you have here is you have bosons trapped in different tweezers. And this can essentially be described by a large angular momentum as n divided by 2, and it's the number of particles that you have in here. And then you can start to abstract this once again in a quantum circuit where we have different operations which allow you to locally manipulate these bosons. So for instance, you would have, here in a second, rotations around the different axes of this large spin. And then you can also have interactions that allow you to have these large collective spins interact with one another. Experimental status for this is this has been demonstrated with up to around 5 tweezers. You can also use it, for instance, to do simulations of, for example, U1 gauge theories. A quick example of maybe a circuit in this particular setting. What we were looking at here is spin squeezing in one large collective spin. What you can do is you can start up with a collective state here, coherent state. There's no quantum correlations in here, you don't have squeezing. And then when you start to act this type of quantum circuit on it, you can look at how this state gets squeezed in this large Z angular momentum. And then this kind of shows you the type of statistics of states that you would measure once you've acted upon this. So it's a nice little community project. It kind of gives you a circuit description of systems beyond qubits. It can be extended to other setups for fermions and spins. It provides simulators for theoretical research and also educational tools. And this is something that could be leveraged now also to sort of abstract away cold atom experiments in a quantum circuit language. So of course, there's a lot more that can be done in this community project. We could start thinking of ways to perform transpilation on these, or manipulate the gates, simplify them, maybe provide a pulse level description of these systems as well. And then think a little bit about how this might look like with algorithms. So with that, I'm almost at the end here. Just like to remind us what we looked at. We looked at a very quick introduction to quantum computing, a little bit the applications, and then the software stack. And with that, I'm at the end, and I will leave you with a roadmap, but there's quite a few things to look at on here. Thank you very much.
you, Daniel, for the night before. And we have time for maybe one or two questions.
And I, yeah.
Sure.
So thank you. So one is like when you sort the data in the beginning using 120 qubits. So there was no error correction in that one. So that's why you call it noisy.
Exactly. There was no error correction, but there was error mitigation. So error correction in principle allows you to have a computation in which the gates are ideal, but it requires a large overhead and physical resources. Error mitigation is a little bit different in the sense that you try and learn some of the noise properties of the device and then undo them on average on the expectation values that you measure.
And could you also say, please, like this 20% difference between classical and your computing data? This data, is it coming because of your error mitigation is not able to really deal properly with it, or is it more classical side that has limitations? Like it's not yet.
Right, it's both. What I wanted to say with this 20% is that all the different methods that were collected together, the different classical methods and the quantum, they agree with each other up to around 20%. And what is particularly new here is that when you look at smaller scale circuits, you can exactly calculate what the outcome should be on classical. There was one single classical curve. And now we're sort of coming into a regime where this is no longer the case, where the quantum systems are hard enough that the classical methods have to make approximations. Different methods will lead to different classical results.
Can you tell us something about the connectivity of the IBM and how much of the challenge it is to scale?
Definitely. So we can't see this on this slide. I could go back, but I think it might take a little bit of time. The connectivity that we have is what we call a heavy hex topology. So the qubits are organized in hexagonal rings, and it's heavy in the sense that 1 out of 2 qubits has 3 neighbors, and the other one has 2 neighbors. The reason why we choose this topology is that it mitigates crosstalk between the qubits. So ideally, from the perspective of an algorithm, I would like to have all-to-all connectivity. But if I do that, first off, it's a massive engineering challenge because you can't structure it, right? And then second, you have this crosstalk, right? I could consider a lattice that is a bit more dense, right? But then you'll have more crosstalk between the qubits. And the reason why we chose this heavy hexagonal lattice is because there are error-corrected codes that you can run on this lattice. And now, if you very carefully look at the roadmap, for instance, here in this chip, the Kookaburra, you'll see that there is a lot going through it. And this corresponds to a long-range coupler that should enable a new type of quantum error correction codes that should be a bit more efficient than what was known up to today.
Is the roadmap all 2D? Is there a prospect of building 3D chips?
Right. So we do leverage the third dimension a little bit in the sense that we have the qubit plane, right? So that's the 2D part. But then we use the third dimension to bring in all of the wiring that you need.
But you can't stack.
I think you could probably get a bit creative there, but when you show that to people in the fab, you know, they'll ask serious questions.
One last question.
Yeah, just a short question. So I'm used to university research with PhDs, postdocs. So this is obviously much bigger. How many people work on the hardware and how many people work on the software there?
Right. IBM Quantum is a very large organization. I don't have the numbers in mind. You can go and take a look at all the papers that come out. It's going to give you an idea of how many researchers do that. But of course, behind that, there are a lot of engineers and people working in fab and so on to actually produce these technologies and also scale them up. So I can't give you exact numbers on that, but it is a massive effort. And I would also like to point out that we, at least in Zurich, we work a lot with PhD students too. So we have PhD students in Zurich collaborating with different universities as well.
Thank you a lot again.